We're gonna start temperature and heat. It's unit 7. So let's first of all define the heat. What does heat mean? Remember, heat and temperature are two different physical quantities. Okay, they are not the same. They sound made the same, but they are not the same physical quantities. Heat is the amount of the energy. Okay, heat is the amount of the energy, or the heat is a form of energy. It's measured in joules and it's a scalar quantity. Okay, so heat energy flows from hotter body to colder one. Okay, it flows from hotter body to colder one, heat energy. So to find the total heat energy in a body, we are going to add total kinetic energy and total potential energy body have. Okay, total kinetic energy and total potential energy a body has will give us total heat energy that body possesses. Okay, this here over here, EK stands for kinetic energy and U over here stands for potential energy. Okay, and this symbol over here stands for sum. Okay, total or sum, right? So when we heat up a substance, what happens to the substance? Heat starts from transferring from one place to another one. Okay, the heat transfer starts happening when we heat up the substance. That means the particles of the substance gain kinetic energy and move rapidly. Okay, move rapidly. That means it's going to go faster due to particles gaining kinetic energy. Remember, the kinetic energy was the amount of energy that our body possesses in order to move. Okay, and second of all, the bonds between the particles in the substance are going to be broken, and the potential energy of the particles will increase as well. So when this happens, the substance changes its states. For example, let's say when you heat the ice, what's going to happen to ice? It is going to turn into water. So it's going to change the state from from solid to liquid. Or when you continue heating the water, what's going to happen? It's going to evaporate. So it's going to change the state from liquid to gas state. Okay. So now let's define the temperature. We said like the amount of energy it's going to be, or the form of energy is going to be heat. What about the temperature? So temperature is a measure of hotness of a body. Okay, hotness or coldness of a body give us the temperature. Okay, the SI unit of temperature is Kelvin. Okay, so the temperature of a substance we measure the average kinetic energy of the particles will give us the temperature of a substance. Okay, the average kinetic energy of the particles within the substance will give us the temperature of the substance. Okay, so here in this figure over here, you may see there's a sparkle over here. Okay, but when you check it out, the water is going to have more heat energy than this sparkle over here. This sparkle is burning normally, but when you think about it, you can say like the sparkle has more more heat energy. But on the other hand, in reality, the water has more kinetic energy than the sparkle over here. Okay, so it is important to notice we use the kinetic energy. Okay, average kinetic energy. We don't use the kinetic energy, we use the average kinetic energy of the particles. So in any substance, some particles will be moving faster than the others. So these particles will have more kinetic energy than the others. Remember, kinetic energy, the energy in motion. So that means when a body move faster, that means that body has more temperature than the others. Okay. So we have temperature scales. There are 3 temperature scales that we are going to talk about it. You already know about the Celsius scale. We generally use in daily life Celsius scale, especially if you don't live in US, or in US you're going to use the Celsius all over the world. There is also Kelvin and Fahrenheit scales. Okay, Fahrenheit scale is used commonly in US. Kelvin scale generally it's the SI. Kelvin is the SI unit of temperature. Remember that. And Kelvin scale that used generally in the laboratory. Okay, Kelvin scale. So these 3 scales are the temperature scales that we are going to learn about it. So for the Celsius scales, Celsius scale, a temperature scale where the freezing point of water is fixed, which is 0 degrees, and the boiling point of water is 100 Celsius degrees. Okay, the boiling point and the freezing point is fixed for this scale. freezing point is 0 degrees, and the boiling point is going to be 100 Celsius degrees. Okay. For Kelvin scales, we use absolute zero. What does absolute zero mean? Absolute zero means one Kelvin scale is 0 Kelvin, which is equal to negative 273.15 Celsius, which is very low. Till now in the world, the minimum temperature measured as negative 269 degrees, which measured in the South Pole. Okay, which measure in the South Pole. So basically, still the scientists couldn't measure the absolute zero. Okay, absolute zero. So absolute zero, there is no thermal energy there. When you get the absolute zero, there is no thermal energy. What does thermal energy means? That means there is no heat energy. Okay, for the absolute zero part. When there is absolute zero, there is no heat energy. So the Kelvin scale, again, we said use the absolute zero. It is a fixed point. It is equal to negative 200 over here, as you see, negative 273.15 Celsius. If you reach this temperature, you're going to die for sure because it's very low. Okay, even though nothing can live, I think, at this temperature. Okay, nothing. It's very low. So we use the symbol K. It doesn't have degrees on it. Okay. Fahrenheit and Celsius, they have degrees on it. As you see here, Celsius has degree on it. This small round dot is as we call it degree. Fahrenheit also has degree, but Kelvin scale do not have any degrees on it. Okay, it's just capital K. All right. So what happens when a substance absorbs heat energy? So what does absorb mean? For example, first of all, let's define the absorb. It means taken in. Okay, when a substance take heat energy, let's say. So when a substance take the heat energy, the particles are going to vibrate more. Okay, for a solid state. So they are going to move faster. That means in a liquid or gas state. Okay, as the heat energy converted into kinetic energy. So remember, kinetic energy is going to make the particles move faster and faster. So this is going to cause the temperature rise on the body. Okay, temperature will rise when you heat the body, when you give more energy, more heat energy to the body. So when particles gain the energy, we can see that they move further apart from each other. So they're going to change their states. For example, if you are heating up a solid, it is going to change its states first of all to the liquid states, and then when you heat more, it's going to change the states to gas state. Okay, which means the substance will expand, increase in size. Think about water. Think about ice. Let's say you have a cube of ice. When you heat that ice, what's going to happen? It's going to turn into water, so it's going to expand. Okay. So the expansion of the substance on heating is called thermal expansion. We are going to call this expansion thermal expansion. This happens in solid, liquids, and gases. It happens in these three states of matter. So let's talk about the thermal equilibrium. We learn about equilibrium. Equilibrium means like in force, we learn about equilibrium. So thermal equilibrium means basically when two different body have the same temperature, okay? When two different body. For example, when you touch at a table, you are going to feel cold or hot according to your body's temperature. You're going to feel like the table, or like when you touch your phone, for example, when you touch it, you're going to feel like your phone is cold. What does that mean? That means your body is hotter than the phone. So when you hold your phone for a few seconds, you're going to feel like your body and the phone are going to have the same temperature after some time. So we are going to call this state thermal equilibrium because you're the hotter body. So you give out the heat energy to the phone. So the phone is going to have now it's going to reach your temperature. So your body and phone are going to be in thermal equilibrium. Okay. So objects in thermal contacts do not have to be in physical contact. Okay, they could be touching each other, but physical contact is not a condition for it. So example over here, as you see, imagine that we have two objects. One of them is 90 degrees, the other one 50 degrees. So when they are in thermal contact, when, let's say, when both of them reach the 70 degrees, heat is going to flow through body A to body B, okay? From body A to, because body A is hotter than body B, right? So the heat is going to flow from hotter body to colder body. So what's going to happen? Then when they have the same temperature, when they reach the same temperature, the heat flow will stop, okay? The heat flow will stop when they reach the thermal equilibrium. All right, so this is the thermal equilibrium when two bodies reach the same temperature, right? Okay. So the first law of thermodynamics. Let's go to over that. So it is essential, the law of conservation of energy. We learn about it. Remember, energy cannot be created or destroyed, but can be transformed into other forms. Like, for example, the kinetic energy can convert into heat energy. Okay, or the potential energy can convert into kinetic energy. Okay, so we call this law of conservation of energy. So the total potential energy is going to be equal to the total heat energy plus the work done on the system. Okay, the work done on the system. This is going to give us the internal energy or the potential energy of the body. So internal energy, this is going to be internal energy of the gas. Even though it is the sum of the kinetic energy and potential energy of the particles in the gas, it is essential that potential energy in the gas. So the symbol U, the symbol U is going to represent here internal energy. Okay, we are not going to confuse these two with other part. So it is going to be internal energy. So all these terms are energies and so measured. Okay. So when we talk energy, the SI unit of energy is going to be always joule. Always. The SI unit of energy is joule. Don't forget this. This was the first law. So what about second? What does second law tells us? So second law tells us heat energy cannot flow spontaneously from a material at lower temperature to a material at higher temperature. What does this mean? That means when you take the ice, the heat energy cannot flow from ice to your body. It is going to flow from your body to ice. Okay, so this is known as second law of thermodynamics. So energy must be used to usual flow of heat energy. This principle is in refrigerators, freezers, and air conditioning units. Okay, this principle is used in refrigerators, freezers, and air conditioning units.
Mister, I can't hear you.
So expansion of solid liquids and gases. So what happens when you heat up the solids, liquids, or gases? So they are going to expand. First of all, let's start with solids. So when you heat up the solids, first of all, linear expansion will happen. What does linear expansion mean? It means the object will increase in size. Okay, in size. The object will increase in size. So we call this expansion linear expansion. As you see over here, there are two metal rods. The first one, it has T1 temperature, and we call it L1. Okay, when you heat up this L1 as T2 temperature, it is going to expand this much. So we are going to call it delta L. So this is going to give us the amount of expansion, and this expansion known is linear expansion, because as you see, the size of L1 is smaller than size of L2 due to heat. Okay, so the linear expansion happens because you heat the solid. So the rod's temperature is going to increase from by delta T. What does delta T means? Delta T means the amount of the second temperature minus the amount of first temperature. When you subtract them, you are going to find the amount of temperature increase inside of a metal rod. Okay, so we are going to what about the amount of extension? We are going to find the amount of extension like this. So this LC stands for the length of the object before heating, and LH stands for the length of the object after heating. Okay, when you heat the object, you're going to have LH length, and before heating the object, you're going to have LC amount of length of the object. Okay, so for an increase in temperature of delta T, the fractional increase is going to be like this. If you want to find the fractional increase, so it is going to be the change in LH minus LC, the change in length of the object over the first length of the object. For example, here, let's say we have a 50 centimeter rod, and it's going to extend by 2 centimeters, so it's going to be 52 centimeter. So what is the amount of what is the fractional increase in the length? So first of all, we have 52 centimeter over here, right? 52 centimeter. So we can divide 2 over 50. When I divide 2 over 50, okay, 2 over 50 change is 2, and over 50 centimeter, because this is the first what do you say? This is the first length of the object. When you divide it, you are going to find around 1.1 over 25, or 0.04 centimeter, 0.04 fractional increase. Fractional increase does not have any SI unit. Okay, why? As you see over here, the length of the rod before heating and after heating has the same unit, which is centimeters. So when you divide them into each other, they're going to cancel out each other. So that the fractional increase will not have any SI unit. Okay. All right. So let's pass this part actually. All right. So we have, on the other hand, surface area expansion. Okay. Let's stop here. Actually, let's not make it more.